Morning. So I said in this problems class I was going to go through some of the questions on ordinal arithmetic here. In particular, I wanted to do some of the laws that we'd referred to last time in lemma 344. These are kind of basic arithmetical laws, such as associativity and distributivity. And we saw how to prove these for the natural numbers, and doing it for the ordinals is pretty much the same, except of course we now have an extra case because of the third flavor of ordinals, where there can be these limit ordinals as opposed to zero and successor. So I thought I'd start out by doing this here first this morning. Okay, so I'm going to look at 344, which is on page 37. And let's look at part A. So it's an associative law. And as I keep saying, we prove this by induction, and I suggest using the last variable that appears. So here's the proof. So I'd say by induction on gamma. Here. So when gamma equals 0, I have alpha plus beta plus 0 here. So it's this kind of trivial, really. Beta plus 0 is, by definition, just beta. And this, anything plus 0 equals 0. So not a lot to say there. Now we suppose true for gamma. And we'll prove it for gamma plus 1. So basically I take here what I want and I try and massage it to look like the thing on the right-hand side. Okay, I look at the definition of what adding beta onto things is. And beta plus the successor of a thing is the successor of beta plus the thing. Right? Here. And now I've got alpha plus a successor of something. So I use the definition of adding alpha there to say alpha plus the successor of something is alpha plus the thing and the successor of that. Now I use the inductive hypothesis to shift those brackets around. There. And now I use the definition of adding alpha plus beta to things here. So the successor of alpha plus beta added to something is alpha plus beta added to the successor of that thing. And of course, that is now exactly what I want over here. So I've done the successor case. So we do 0, we do the successor, and now we do the limit down here. So this is the novelty for ordinals. Suppose true for gamma less than lambda, but I know this. I want it now for lambda itself here. Now I'm just restating here what we want, right? Okay, so I start out optimistically and I write here on the left-hand side. And I use the definition of what beta plus a limit is here. Beta plus a limit is the supremum of the beta plus gammas for gamma less than lambda. All right, I've got tors down here, tor less than lambda. And that is literally the definition of what it means to add a limit ordinal to beta, once you check that out. Okay, we'll appeal to an earlier exercise. That's 321, part 1. What did this exercise say? Let me write that out on a piece of paper first. Here's exercise 321, right? Which I dare say you've all got in front of you, but I can talk about. Let X be any set of ordinals, then alpha plus sup X is the supremum of the alpha plus tors for tor in X.
Sorry, could you move the page up a little bit?
Sorry, do you mean that? Down? Do you mean down or up?
Down, so I can see the bit above the exercise 3.21. Thank you.
Okay. So I'm cutting away from this proof to exercise 321 here. I probably should have started with this. So the idea of the exercise is alpha plus the supremum of this set of ordinals is just the supremum of alpha plus the tors that are there in X. So how am I going to apply that here? Right? Here I've got alpha plus the supremum of a set of ordinals. And the exercise says I can put the alpha inside the sup and the brackets. So literally speaking, what I'm doing is letting X here be the collection of beta plus tors here for tor less than lambda. If I let X be this collection of these beta plus tors for tor less than lambda, and I apply the exercise, alpha plus sup of X here, well, that's exactly what I've got here. Alpha plus the sup of X is just the sup of the alpha plus the ordinals that are in X. Here. So that is 321. So two more lines to come here. Now I use the inductive hypothesis to move these brackets around. Because I know that's true for anything less than lambda. But now this is the definition of alpha plus beta plus the limit lambda. So again, here we've got what we want. We've gone from this one to this one. Okay, so there's quite a lot of, well, there's some detail there, but we're basically using just the basic definitions plus a little bit of side work that's there. So B, 344B is there in the notes. 344C, associativity of multiplication, it's pretty much just writing times for plus throughout here. And then instead of using 321.1 here, we've used 322.2. Alpha times sup X is then the supremum of the alpha times tors for tor in X here. So reading to this exercise then, we can justify these laws that are there, that are down there. Okay, B is there actually in the notes. Don't necessarily propose doing B unless anybody wants me to do another of these clauses of 344 here. Just say so, and I can do it. Okay, so ordinal arithmetic, it takes a little bit of getting used to. So we've seen various things. We don't have commutativity. here. Likewise, 2 times omega. What is this? This is the supremum of the 2 times n's for n less than omega. So this is just the supremum of the finites. This is omega. And again, omega times 2. This is 2 copies of omega. So this clearly does not equal this. Right? So we don't have commutativity here. We also have phenomena like I mean, it's called additive indecomposability. N plus k is less than omega for any n or k less than omega. N plus omega is omega. After all, what is this? It's the supremum of the n plus k's for k less than omega, which is that. So I can add one order to another, and I just stay with the second one that's here. Okay. So we can have this kind of so an ordinal is called indecomposable, or sometimes additively indecomposable, because it's all about addition. So let's call it sigma. If for any alpha beta less than sigma, alpha plus beta is less than sigma. So example here is omega is indecomposable because you add any 2 finites and you get a finite. Right. So you might ask, well, are there others? Well, in fact, there are lots, right? Think about omega squared. Okay. So this is omega, lots of omega. So if I pick an alpha less than omega squared, so I can think of it as omega, lots of omega here. Each of these is a bunch, is omega. So if alpha is less than omega squared, it falls somewhere on this line here. Then this is saying there is some k so that omega times k is less than or equal to alpha, and it's less than omega times k plus 1. Because alpha appears somewhere, it appears on or after the kth block of omegas, and it's before the next one. So I guess here, how I've drawn it, this looks like 3 blocks here. So anything that's less than omega squared falls somewhere down here, right? So if beta is another ordinal less than omega squared, where is it going to appear? So the sum n where it appears between the nth and the n plus first block. Okay, so maybe beta is here. Okay, but then if that's the case, then if you add alpha plus beta, this is going to be less than or equal to omega times k plus 1 plus omega times n plus 1. By the distributivity law, this is omega lots of k plus 1 plus n plus 1. So that is obviously what it is, k plus n plus 2. But the point is, this is still less than omega lots of omega, which is omega squared. So what we've just done is show that omega squared is also additively decomposable. I pick any two things, alpha and beta less than omega squared, and their sum is less than omega squared. So note also from that. Another way of putting this is to say if alpha is less than omega squared, then alpha plus omega squared equals omega squared. I'm just getting some more paper. Let me write that out again. Because again, if alpha is less than omega squared, there is some k such that alpha is between the k and the k plus first block in our picture. So alpha plus omega squared is less than or equal to omega times k plus 1 plus omega squared. So here we're using if gamma is less than tau, then gamma plus anything, mu, is less than or equal to tau plus mu. So alpha plus omega squared, if alpha is less than this, it's going to be less than or equal to this plus this here. But going from here, again, so let me write it out once more. I can think of this as omega squared as this here. Now I use the distributive law. I think of that as omega lots of k plus 1 plus omega. I'm using the distributive law there. But now k plus 1 plus omega is omega. And this is omega squared. So altogether, I got alpha plus omega squared is less than or equal to omega squared. Right? Well, that must mean they're the same. And certainly omega squared is less than or equal to that. Right? So we have equality. So we've seen then for this additive indecomposable omega squared, anything less than it added to it is itself. And we've also seen you pick any two things less than omega squared, then their sum. That's what I was doing back here. I pick an alpha or beta less than omega squared, and then their sum ends up being less than omega squared here. So if you then think a little bit more about this, omega squared times 2, again, this is not indecomposable. Since omega squared is less than omega squared times 2, so this is my alpha, if you like. Omega squared plus, here's something else less than omega squared times 2, right? This equals omega squared times 2. So I've got two smaller things than omega squared times 2 that add up to it. We have alpha, and in this case equals beta less than omega squared, with alpha plus beta equals omega squared times 2. So if you asked to show that this is not indecomposable, you'd say something like this. Yeah. So in the same thing for omega squared times 3 times 4 times 5, a similar argument. So the next indecomposable after this is not indecomposable. So the next one is omega squared times omega, which is omega cubed. And now, if you have something that's less than omega cubed, it falls in some omega squared block. So we reason as before. I'd use the same picture here. I've got omega blocks of, now these, each picture here is omega squared. So this is my picture of omega cubed, omega lots of omega squared. If something is less than omega cubed, it now falls between two blocks like this. So there's a k less than omega, where now I write omega squared times k is less than or equal to alpha, might equal alpha. And I could do exactly the same moves that I just did before. Okay. So just I see there's some questions on chat, which I'm not ignoring. I'm just saving them for a moment. So there are exercises about the indecomposables there. You'll find in the notes. I mean, there are ideas about multiplicatively and exponentially indecomposable. I mean, you could leave those for now. That's perhaps something to come back to. Okay, let me look at the questions in the chat. So a simpler one to dispose of is why is 2 times omega equal to omega? Well, you look here at the definition of multiplication. What it means to multiply something by 2 here. And this is the case of we're multiplying a limit ordinal here by 2. So the question is what is this? This is what we're going to write more informally as this. But this is by definition the supremum of the 2 times k's for k less than omega. Right, if this was some other limit ordinal, lambda, I'd be putting here 2 times tors for tor less than lambda. For general limit ordinals lambda. And what is the supremum of these? Well, these are just the evens here. This is just omega. So this is why 2 times omega comes out as omega. Yeah. Look at 2 times omega plus omega. This is another limit ordinal. So this is the supremum of the 2 plus tor, 2 times tors for tor less than omega plus omega. Right? Here I'm just applying the line above with this. So in fact, what are we going to get out of this? Right? This is 2 times omega plus 2 times omega, right? By the distributive laws. Distributive law, sorry. We've already seen that this is just omega plus omega by the above over here. So indeed, 2 times omega plus omega, it's omega plus omega here. In general, for lambda limit, right, 2 times lambda will be lambda here. Okay, the other question in the chat is, so yeah, indeed. So limit ordinals, I mean, what have we got? Just to recap, 0, we then have some successor ordinals here. So omega here is the first limit ordinal. Then comes omega plus 1, omega plus 2, and so on. And then here comes the next limit ordinal. It's because it's the supremum of the omega plus k's, right? It's not the successor of anything, it's the union of the previous ones. And continuing, there'd be an omega plus 1, and so on. And the next limit would be omega plus omega. So we'd start writing this as omega times 3. Right? It's 3 copies of omega. This is omega times 2. And then after a while, the limit ordinals start crowding up. There's omega times 4, omega times 5. And then after we've got omega, lots of omega, we've got omega squared. So omega squared, in fact, is the supremum of the omega times k's, for k less than omega. And the picture continues, right? So I'll start, here's omega squared. There's going to be, well, the next limit ordinal here is omega squared plus omega. And then after a while, we're going to have omega lots of these. So we're going to have omega squared plus omega squared. Or omega squared times 2. Then these will proliferate. We'll have omega squared times 3, omega squared times 4, and then we'll get omega cubed. Etc. Right? So eventually there's going to be omega to the 4, omega to the k, we go all the way up here, and then the supremum of all of these, this will be omega to the power omega. Here. And of course, we're not yet done. Right? This whole picture goes on forever. Right? Okay, the first question that came up from Rokas, right, is how do we define ordinal addition using transfinite recursion in the second form? Okay, so let's see what we are discussing here. So this is page 34. So let me put up here what we're looking at. So it's looking a little bit dim. Yeah. So recursion theorem on the ordinals. So it makes it look a little bit more like addition, or sorry, just recursion on the naturals. In this form, we take a starting point. Our eventual function is called h. The h of 0 is going to be this starting point here. And we have two functions, right? And f0 is going to tell us what to do at successive stages here. And f1 will tell us what we do at limit stages. So our function from ordinals, h, would behave differently if we're talking about h of a successor or h of a limit. So if alpha is beta plus 1, a successor, we apply f0 to the previous value that we knew. For alpha limit, we say that h of alpha is f1 applied to all of the previous values that we've got, h restricted to alpha here. So I guess your question is, how do I make my definition of addition look like this? The proof here, which I did go through before, shows how to convert this form into something that looks like the form we proved, the first or more general form. So addition was just performed like this, of the successor of something, this was just going to be A alpha of beta. We take the successor of that. So commonly we were going to write this as alpha plus beta plus 1. This was going to be alpha plus beta plus 1. Yeah. And then in the limit case, here, this we define to be the supremum of the A alpha tors for tor less than lambda. So this is the supremum of the, and we agreed to write that like this. And this was going to be alpha plus lambda. So the idea here is that in our recursion theorem second form, right, f0 here is just the successor function itself. We're defining h of the successor of beta to be f0 of h or beta, and this is just going to be the successor of. And h here is my A alpha function that I'm aiming for. Sorry, it's here. Right, so that looks like this here. Now for limit cases, we want f1 function to be something that's of all the previous values. So I could just say let f1 be, I look at the function I've already got, A alpha restricted to lambda, right? So this is my h restricted to lambda. And what do I want f1 to be? I want it to be the supremum of all these alpha plus tors here. So I would just say that f1 be the sup of the range of this. So let f1 in general of a set here be the supremum of the range of u. Right, if u is a function. Right? I could let it be empty otherwise. So now alpha plus lambda is f1 of the function up to a alpha restricted to lambda. So this is going to be the sup of the range of the function like this. The range of a intersect a restricted to lambda is this stuff here. Which is indeed just how we defined it. So this is how you would justify addition based on that second form of the recursion theorem. We'd say here is the starting point. This is my h of 0, my starting point. The f0 function is just, in this case, the simple successor, and that tells us how we get h of beta plus 1. And here we have h of lambda, which tells us we apply this sup range function here as in my f1. So we can massage this addition definition into the recursion theorem in the second form. And the same for multiplication and exponentiation. It's pretty much just changing of letters here from A's to M's and so on. Okay, hope that was all reasonably explicable. I've set just 3 exercises, of course, each time, but I do advise you to try some more of these exercises that are down here. It takes a little bit of getting used to this ordinal arithmetic, right? So practice, I think, is what's your watchword here. Okay, fine. Do keep sending questions, as I say, and next time we will start chapter 4 on Cantor's other contribution to the study of infinite sets. That's the study of cardinality or infinite size. So I'll see you this afternoon.